Hey everybody, so I know that whole idea of resolving things into components, your X's and your Y's, all that stuff, that goes over people's heads a lot of times. So what this particular video is, it's only got two slides in it. This one and a practice problem. We're just going to go look at that one more time and kind of walk through it a little bit more. If you don't need the help with it, if you think you kind of got it, you can sit back and have a snack. But I'm going to take a look at this vector components method one more time. Here's our list of steps that we had from the end of the last video. So I would really strongly recommend that you put these notes, on a sticky note or something like that. Have it next to you as you're trying to walk through this. So the whole idea with this is we're trying to add some vectors together, right? And these vectors at some random angle. Rather than trying to do a bunch of complicated trigonometry, this feels complicated enough as it is, right? What we're going to do is we're going to use the idea that every vector, no matter what its angle at, we can talk about it in terms of its x component, or sorry, that's y component, and its x component, right? Every vector, no matter what its angle is, has an over and it has an up. So all we're going to do is use sine and cosine to figure out what that x component is and that y component is. And then we're going to take advantage of the fact that, well, if we've got two different vectors, they both have some overs and some ups. I can add the x's together. I can add the y's together and get an overall x and an overall y. And once I have those two things, I can use Pythagorean theorem to figure out what my one single path would be. So again, I know this is a little bit overwhelming at times for students when we first start doing this. Some people get it right away, but a lot of people are like, what are you talking about? And it takes a few examples of working through this. And when I work through it, it's not fast, unfortunately. It takes a little while to go step by step by step. So hit pause if you haven't already done so. Write these on a sticky note if you didn't get them from your notes in the last time. So you've kind of got it out, and you'll see that I'm going through these steps as we get going. So here's our practice problem that we're going to use right now. So again, use these steps, and we'll kind of figure out how to address it. So here we've got two little vectors. We've got a blue vector and a red vector. Nice English. One's at 25 meters, which is due east. And then the other one's at 15 meters, which is at some sort of angle. I'll put the angle in here in a second. Forgot to write that on there. At some sort of an angle. So let's say that this angle right here, what do we want to call that? I don't want it to be a 45 because that's too easy for us. I'm going to call it 55 degrees. This would be north of east. 55 degrees, a little bit steeper than that, but we'll call it good for what we're doing right now. So we'll say that is our angle. So 55 degrees north of east is right here. So in this particular example, I've only got one vector that needs to be resolved into x and y components because one of them kind of already is. And I'm only doing that in this case to kind of make our practice problem here a little bit shorter so that we can kind of work through it a little bit faster. So we've got our two vectors. They are both drawn at tip to tail. I'm going to do this 55 degrees north of east so I can get it out of the way. Oops, sorry, eraser. Get my eraser there. So at 55 degrees north of east, the next part of our steps is to sketch the resultant vector, kind of figure out where it is and what direction it's going. So I'll use green for our resultant vector. And so here it is right here, like that. That is our resultant vector. That's what we're trying to find. It's the single straight line vector from start to finish. And no matter what the two or three other vectors would be, the single straight line vector from start to finish is called our resultant vector. So if you take a look at this, our resultant vector has an angle to it, and it has a length to it. So that's what we're trying to find. And if we have this, I'm going to kind of redraw it over here. I'm going to try to draw the same vector. It's going to be a little bit off. Let's say this is also R. Angle's a little funky on there. There is, for this resultant vector, there is an x component to our resultant vector and our y component to this resultant vector. So what we're trying to find here is, well, what is this? What's the total amount of x, the total amount of horizontal movement that this vector has gone? So it's actually this. And then for our y, it's what's the total amount of up that's gone. So it's actually the sum of our y's. So that's kind of the direction that we're going with this. How much total to the left or to the right did we go? How much total up and down did we go to figure out what those different pieces are? So we're going to do this one vector at a time. We'll do the blue vector, then we'll do the red vector, and then we'll try to figure out what our components are and how they add together. So I'm going to switch to blue here. So for our blue vector, which is vector number one, it's 25 meters. What's the x and y component of our first vector here? Well, it's actually kind of easy. The x component is equal to 25 meters, or meters, because it's all x. Our y component is equal to 0. There is no up and down to it. So that makes it a little bit easier, so we don't have to do all the crazy resolving things into component stuff. We just have to deal with the red one. So let's take a look at our red vector, which is 15 meters, and it's at right here, 55 degrees. So again, that's what we're kind of looking at here. This is this red vector right here. So to figure out our x for this and our y for this, we have to resolve this, because there is some x to it in the positive direction and some y to it also in the positive direction. So that's what we're trying to find. So our x side, think to yourself, is this the this side right here, the x, is this the adjacent side or the opposite side? Because once you know what that is, that's going to help you decide which sine, cosine, tangent to use. Remember, because it's so, and then it's ka, and it's toa. So with the opposite side, we use sine. With the adjacent side, we use cosine. So in this particular case, our x component is the adjacent side. So we're going to use cosine in this case. So in order to do this, we're going to do cosine of our angle, which is 55 degrees, is equal to the adjacent side, which is our x, divided by our hypotenuse, which is 15. Again, double check to make sure your calculator is in degrees and not in radians. And then you do the math. Cosine of 55 times 15. I'm literally doing the algebra at the same time. So because we have 15 on the bottom, we multiply this side by 15. We multiply this side by 15. So our answer for that is, I'm going to do 2 digits for this one, 8.6 equals x. And this would be in meters. That tells me this side right here is equal to 8.6. Now let's take a look at our y. Okay, our y is this direction. Okay, so we know it's going up. This is our opposite side on our triangle. So now we know we're going to use sine instead of cosine, because sine is opposite over hypotenuse. So this would be the sine, it's not really equal to, it's an arrow there. Sine of 55 degrees equals our y component over 15. You're always going to use them, each one. You're always going to use cosine for one and sine for the other one. The trick is to know kind of which one's which, and it depends on which way the label is or where the angle is being identified. So you just got to kind of take a look at that triangle. Is it the adjacent side? Cosine. Is it the opposite side? It's sine. In this case, it's x and y. So the sine of 55, let's see, the sine of 55 degrees times 15 is equal to 12.287. So approximately with 2 sig figs, 12 meters equals y. Okay, so what does this tell us now? This tells us that looking at our little triangle up here, here's our 15-meter vector. Our x component for this right here is equal to 8.6. 8.6, and our vertical component is 12. So this one's just 25 over, the blue one. This one is 8.6 over and 12 up, if you want to think of it that way. So now we want to look at our total of our x's and the total of our y's. So I'm going to kind of start to switch to green here. So to figure out the total amount over that a resultant vector has, it's got this 25 meters here plus the 8.6 meters from the other triangle. So it's got 25 plus 8.6. So the sum of our x's is going to be equal to 25 meters, because that one was all x, plus 8.6. 8.6 meters. And again, those were 2 different vectors. And so what's our value for that? Let me figure it out. 25 plus 8.6 is equal to 33.6. Is equal to 33.6. That's this value now, equals 33.6. All the way 25 meters over, plus another 8.6 meters over from the second vector. Okay, how about the sum of our y's? Okay, well, our first vector didn't have any up. Well, that's kind of handy. And again, I just did that to make this one a little bit shorter. So 0 meters up from the first vector, plus our second vector did have some up, right? This one, the red vector, had some up to it. In fact, it had 12 meters of up. So 12 meters. And that gives us the sum of our y's is equal to 12 meters. In other words, this right here, the only up that happened was due to that red vector. So this one is equal to 12 meters. Again, lots of times you're going to have two different angles, right? That you're going to have, blue would have both x and y, and the red one would have both x and y. I just kind of shortened it up in this particular case. So now, if we know that our resultant vector is a total of 33.6 meters to the right and 12 meters to the north, whatever that is, now we can use Pythagorean theorem to figure out what our value is. And so we can use Pythagorean theorem, x squared plus y squared equals r squared. So this is 33.6 squared plus 12 squared equals r squared. A little bit of algebra here. 33.6 squared plus 12 squared is equal to 1272.96. I'm going to take the square root of that value. And I get an r value equal to 35. Basically, we're going to call that 36. Again, we're just doing it with one sig fig. So 36 equals r, and that's meters. So we now know this is 36 meters. Again, x squared plus y squared equals 36. Again, with sig figs. Okay, last part that we need to do. Again, this is mentioned on that previous video. We need to describe what our angle is. We've got the magnitude of a resultant vector. Now we need to analyze, well, what direction do we walk 36 meters in? We need to know the angle here, and we need to describe the direction of that particular angle. So I'm going to erase a little bit here just to give myself some more room to work. So I'm going to get kind of rid of this components working here. Okay, there it is. So now, in terms of dealing with our final angle here, take a look at this. A lot of times we use tangent. It's a very common thing that we would use. So if we use tangent, tangent is TOA. Tangent equals opposite over adjacent. So the tangent of our angle, this is our unknown. So we're going to call this theta. Tangent of theta is equal to the opposite side, which is the sum of our y's, over the adjacent side, which in this case is the sum of our x's. Again, this isn't 100% always true, but in this particular triangle, the opposite side is the y, and the adjacent side is the x. The x side is actually touching that angle. So tangent of theta is equal to 12 meters over 33.6 meters. And then you take the inverse tangent to get rid of it. So I do second tan of 12 divided by 33.6. And I put the other parentheses around it. And I get a value of theta equal to 19.65. You can kind of see how I have it typed into the calculator there. Sorry, there we go. 19.65. So basically 20 degrees, and you'd have a decimal place there for 2 sig figs. And yeah, this looks like it's less than 45. 20 degrees is a good estimate in terms of what that is. The last thing that we need to do is describe the direction of that angle. Okay, well, that angle is touching the east axis, if you want to think of it that way, or the horizontal axis. So this would be 20 degrees, basically east. But now am I going to the north of east or to the south of east? Again, I'm going east. If I turn this direction, I am going north of east or above east. So we would write this as 20 degrees north of east. Or if this was like horizontal vertical, you could say 20 degrees above horizontal to the right, something like that. So this is how we would completely define our angle. We would say it's 36 meters. Where should I write this? Our resultant vector is equal to 36 meters at 20 degrees north of east. And that's our final resultant vector right there. So again, doing this vector components thing, we're just trying to find the x component of each vector. We find the y component of each vector. We get the sum of our x's and the sum of our y's, and we start thinking about our resultant vector that's on there, the sum of our x's and then the sum of our y's. So again, we're taking each of our original vectors apart so that we can put them back together in an order that makes more sense to us with Pythagorean theorem and sine, cosine, tangent. So there you go. That's it for today. Again, we're going to come back in the next video, and we're going to do a little bit more applications to how we would apply this to force problems. I hope this helped a little bit. Definitely, this is a lot of steps. It's kind of confusing for students. So I hope this helped. All right. See you guys next time.